Yeah,
Yes,
shall we
sir.
start?
Yes, sir.
One second. Yeah, okay. So next we'll see uh, thermodynamics of reduction process. Okay, overall, what are the processes we have? How do we, what are the processes involved in the reduction that we discuss? So next we are going to see thermodynamics involved in the reduction processes. So heading you write down thermodynamics of dynamics of reduction process. In this only we have Ellingham diagram. Okay, Ellingham diagram will discuss what it is, but you need to just understand like 2-3 information that we can extract from Ellingham diagram. Okay, it is basically the plot of or the graph of, write on the heading Ellingham diagram. It is basically the graph or plot of delta G naught, delta G naught, and temperature. Okay, graph of delta G naught and temperature. Delta G naught versus temperature. And in this, what happens, the reaction we are considering is the formation of oxide, formation of oxide of various elements. Right on these diagrams can be used to predict can be used to predict the feasibility of the thermal reduction of an ore. The thermal reaction, we write down. thermal reaction of an ore. Like if you have any reaction, suppose M solid we have, it combines with oxygen. Basically, it is a formation of oxide. So we can also do this for halides and sulfides. Ellingham diagram we can draw. In the syllabus, and mostly that they ask is for oxides. So we are discussing oxides only. M plus O2 gives a MXO. 2 I'll write down here, 2X this side. Two X. So you see here what happens. This oxygen is a gas. It is converting into solid. So since we have the reaction of the graph of delta G naught and temperature, correct? So could you tell me in this reaction, what could be the change in entropy? Delta S naught, greater than 0, less than 0, or 0?
Less than 0.
Less than 0. So delta S, since gas will have more entropy than solid, gas is converting into solid. So we say that delta S, the entropy change is negative. Correct. Okay, which means if delta S is less than 0, which means delta G naught becomes less negative. Yes or no? Because delta G naught is equals to delta H naught minus T delta S naught. So delta G naught becomes less negative here. So it increases with temperature, correct? This means as temperature increases, delta G naught increases. Correct? That's the first thing that we have. So we need to understand the relation of delta G naught and temperature only.
So do we have anything about entropy then?
So entropy
Enthalpy of reaction, sorry.
Enthalpy, whatever it is, see, enthalpy, whatever it is, delta G naught, delta H naught minus T delta S naught. Right? So if this is negative, so overall delta G will increase only, no? Means enthalpy change, enthalpy change is there, but that is not a major effect here. This becomes positive, so delta G is increasing.
Oh, okay, sir.
Next, one more line you add over here. Next line, the free. Once again, the free energy change that occurs when 1 gram molecule of a common reactant the free energy change that occurs when 1 gram molecule of a common reactant, which is oxygen here, because we are talking about oxides, correct? So common reactant in bracket write down oxygen, the free energy change that occur when 1 gram molecule of a common reactant oxygen is plotted against, wait a second, 1 gram molecule oxygen is plotted graphically against temperature, then this graph is known as Ellingham diagram. Correct? So delta G naught for 1 gram of substance plotted against temperature. So the graph is called Ellingham diagram. Okay. We can do this for halides as well as sulfides. Okay. But there we have the reaction of sulfur and halogencium. But in the syllabus we have for oxides only. Correct. We have also seen delta G naught increases as increase in temperature. That's one thing. Now, if you look at the graph, I'll show you the Ellingham diagram here. Yes, I have. So this is the Ellingham diagram we have, you see. It is given in NCRT also. You can open up and see. It's fine, visible, all of you?
Yes, sir.
So this is the graph we have. You see, it is 0 degrees Celsius. And then delta G naught is increasing. Negative, the value is increasing, correct? Here, temperature is increasing. You see, for all the reactions, MgO, Mg plus O2, we have a positive slope, and then there's a sharp change in the slope. We have this also, slope increases, slope increases, slope increases. For this carbon, the slope is decreasing. Okay, so mostly for all the reaction you see, the slope increase. We have positive slope, right? With the graph going up, with increase in temperature, delta G naught value is increasing. And at some point, we have a sharp change in the slope here. This is what the observation we have, right? So when you calculate delta G for all these reactions at different temperature, this is the plot we get. Correct?
So, but why does it increase sharply for some, not at all increase, and decrease also
Yes.
for some?
Yes. 1 second. We'll discuss.
Sure, sir.
Write down the this you don't have to draw. If you want, you can roughly you can just draw. Okay, but it is given in the roughly you just draw, because when you refer your notes, it should be there. Okay, so roughly you draw for a few reactions. Like carbon reaction, you must draw. Okay, magnesium you must draw. Okay, we have somewhere Hg also. Hg, carbon, magnesium you must draw. CO2 also you draw. Correct? Done? Let me know once you're done.
So the carbon one is a straight line, like horizontal line.
Carbon one.
Yes, sir.
Yes.
Okay.
We have two reactions here. One is it is forming carbon dioxide, and other one is forming monoxide. Done, finish. Okay, so I think you are done. Yeah. Okay. Now you see, we will discuss why this sharp change we have over here. Sharp change we observe whenever there is a phase change. Okay, like you see at this temperature, why we have this sharp change over here? Because at around 630 Kelvin, this mercury boils. Okay, so Hg boils at this temperature. Hg boils at this temperature. That's why we have a sharp change in this. So wherever we have the sharp change, it represents the phase change of the reaction. Magnesium also at certain temperature, which is this here, at this temperature, magnesium also boils. Okay, because continuously we are increasing temperature. So we must have the boiling point of metal, correct? So it will boil at this temperature. So whenever we have the sharp change, it represents the phase change of the reaction. Correct? Understood this point?
Yes, sir.
Sharp change is this. Second point you write down, which is more important. Metals which lie above in the Ellingham diagram metals which lie above in the Ellingham diagram get reduced by, okay, properly write down this, okay. Metals which lie above in the Ellingham diagram get reduced by the metal which is below. get reduced which is below. What do you mean by this particular line? जैसे देखो magnesium and aluminium है, so what I said, metals which lie above get reduced with the metal which is below. So magnesium can reduce aluminium. Okay, magnesium can reduce aluminium till the temperature is around 1623 Kelvin. Okay, 1623 Kelvin roughly. Because at this temperature now, beyond this temperature, you see the magnesium line is up and aluminium is below this. Correct? So reduction of aluminium is done by magnesium when the temperature is below 1623 Kelvin. This is the another information we have. If you talk about this one, silicon and magnesium. So it is possible till 1966 Kelvin, till this point. Till this temperature, magnesium can reduce silicon, but beyond this temperature, it is opposite. This is the property, like, the features of Ellingham diagram. Whatever graph is there up, like all metals which are placed, or the graph which is there below one particular metal, so the upar wala we have the metal, the graph which is above, that metal will get reduced by the metal which is present below in the graph. Right? So temperature based reaction it is, right? It's not like it is universal, always it happens. It will be there for a certain temperature and then it may get changed. That is the second point over here. Third feature in this you write down that we easily see, that gives free energy change increases with increase in temperature. Increases with increase in temperature. Fourth point. Fourth point. The sharp change in the slope or turn, you can also write down the sharp turn in the graph. Better written, the sharp change in the slope represents the change in state. The sharp change in slope represents the change in state when the metal melts or vaporizes. Right? Melts or vaporizes. Another very important point, you see this line you consider corresponding to delta G is equals to 0, this line. Right? You see below this line, for all the reaction, delta G is what? Less than 0. Correct? And when delta G is less than 0, it is spontaneous and the oxides are quite stable. Can we say that? Obviously, we have certain temperature for all the reaction. You see this graph is also going at some temperature, it will cross the line, right? This graph is also going like this. At some temperature, it will cross the line. So when delta G is less than 0, till that temperature, the oxide of a certain metal is said to be stable. But when the delta G becomes positive at any temperature, then the oxide is not stable and it can easily decompose into its metal. Are you getting it? Right? So this point first you write down. Below delta G is equals to 0 line, below this line where delta G is equals to 0, below this line delta Z is equals to 0, the oxides are stable. And when delta G becomes positive, And when delta G becomes positive, the oxides become unstable and dissociates into metal. Dissociates into its metal. Okay. Now the last property here, why this carbon will have two types of graph, right? We have graph here for carbon. One is we have minimal change or there is no change in delta G when it forms CO2. And then we have this negative slope. The graph goes down like this when it forms carbon monoxide, that is CO. So write down to this. Write down the carbon with oxygen. I'll write down next slide. Carbon with oxygen shows two types of reaction. One is when C plus O2 gives CO2, suppose this is a reaction 1, and the another one C plus half O2 gives CO, the reaction 2. Correct? Okay. Now, if you look at this reaction, we have carbon solid, O2 gas, CO2 gas. Okay. Gas, it is CO is also gas, it is solid. So see in first reaction what happens, right down in first reaction, the volume of CO2 obtained is same as the volume of O2 used in the reaction. Volume of O2 used in the reaction. Correct? So you see 1 mole of this gets consumed and 1 mole of CO2 forms. So if you look at delta S change in entropy here, it is minimal, right? Almost zero. Correct? Because we have two different gas, so we cannot say delta S is equals to 0, but the change is not that great. Okay. Hence, what happens? Change in delta S is minimum over here. That's why the Gibbs free energy change, delta G naught, is also minimal. That's why if you go back and see the graph we have here, in the graph, you see the change in delta G is minimal for CO2. You see it is almost a straight line or slightly decreases, almost minimal. Yes. So this is for the explanation for the first, reaction of CO2. Correct. Now, what happens in CO when CO forms? You see, you can easily understand the number of moles in this reaction. We have this reaction. So half moles of O2 consumes 1 mole of CO forms. Correct? Or the ratio is like 1:2. 1 mole of O2, 2 moles of CO. 10 moles of O2, 20 moles of CO. So 1:2 ratio we have. Correct? It means for this reaction, what we can say, delta S is positive. Right? Delta S is positive. That's why everything is reverse, ulta over here. Right? So when delta S positive, delta G becomes more negative as T increases. Right down here, delta G becomes more negative as T increases. And that's why the graph goes like this, okay? Like this, the obtuse angle slope we have, correct? Okay. Okay. One more thing I would like to add here. Acha, so we have see here what happens at this point. We have the two reaction, right? CO and CO2 reaction is this, correct? So this temperature is around 630 Kelvin is this, so slightly above this, around 700 or to 710 Kelvin, right? 700, around 700 Kelvin, the reaction gives CO2. We have this reaction because the line is below, right? So around 700 Kelvin, below that, below less than, I write down here, if the temperature is less than 700 Kelvin, approximately 10, 15 degree, maybe upper, niche, maybe there, right? Like increase or decrease, 710, 700, no, 15, maybe there. But if temperature is less than 700 Kelvin, roughly, correct, then the reaction of carbon and oxygen gives CO2. If the temperature is more than this, then it will give carbon monoxide. That is the information we can extract from Ellingham diagram. The point simple here is what? That it gives the feasibility of the oxide forms of various elements, metals, okay, at different temperature. Okay, the sharp change represents the change in phase. That's what we have discussed. The metal which is above in this diagram will get replaced by the metals which is present below. All these things are temperature dependent process. Okay, like you see below this temperature, magnesium can reduce aluminium, but above this temperature, aluminium will reduce magnesium. Okay, so the 3-4 points I have given you, mostly they ask questions on them only, theoretical questions. You just need to understand these 2-3 points. If you keep these 2-3 points in mind, you can answer all the questions based on Ellingham diagram. Okay, done.
Sir,
So it's
what does
basically
change of state represent for the carbon monoxide one?
where
Sir,
this
in
one.
the I can't see your cursor. Oh, yes, sir, that one.
This one, right? So phase change will occur over here.
So before that, carbon monoxide would be liquid.
Yes, and then it converts into gas.
So, but isn't it gaseous at room temperature itself?
We say that, see, when we write down the reaction of CO plus O2 gives CO2, we always write it's a gaseous form. We don't talk about temperature over here. But actual understanding is this, like based on temperature, so because we have some gas, no. So if you have higher temperature, correct, then the kinetic energy of gas will be more. Interaction will be less. Correct. Interaction is less, then liquefaction is difficult. Right. So it is possible that we'll have some liquid form because you see temperature is extremely low. You see, oh no, not this side. The reaction is possible here. You are increasing the temperature, correct? So it is possible that at some point it may get boiled. But usually when we say C plus O2 gives CO2 gas, we don't talk about reaction, temperature over there, no. So state of the compound or molecule that you are getting, it may depend upon temperature because we know interaction of molecules, whether it intermolecular force lies in the range of gaseous state, then it will be a gas, solid state, then it will be a solid, correct? So actual understanding will have this over here. So you can say at less temperature, maybe CO2 will be in the liquid form. We have one more thing here that at some times, this will get boils. At some temperature, metal, melts also, right? The temperature is below. We are talking about higher temperature over here. So all these represents the phase change. Usually why we are confused over here, that whenever we write down the reaction of carbon and oxygen, we don't talk about temperature. We'll say we'll get a gas over here. But yes, temperature is a condition that we need to think of.
Okay.
Correct?
Yes.
Yeah. If you want to understand this reaction, you can, why the slope is this? Phase change, the logic to वही है जो मैंने कहा अभी, correct? If you look at the delta S for this reaction I'm talking about, delta S is what? Less than 0, greater than 0. This is gas, correct? This is also gas. So 3 moles converts into 2. Delta S is decreasing, no?
Yes, sir.
Entropy is decreasing. So with increase in temperature, the entropy will also, the delta G will also, it means normal relation we have, like we had for other gases. Delta G
Yes.
increases. At this point, we'll have a phase change and there is sharp change in the graph. Correct, no? Acha, okay. So we had done all these things. Now we need to see some extraction of some metals. Okay. We have I'll show you the flow sheet. Okay. How to, go through the process of extraction of like copper and extraction of silver. Obviously we have zinc and other metals also. So all we are not going to do because not that important, since we have discussed the the basic process, what all steps we have in extraction of metals. We have seen concentration of ore, different methods into that, calcination we have seen, roasting we have seen the reduction method. So all those methods only we are going to use for any metals. But yes, there may be few changes, few process will be different here and there, but more or less we'll have the same thing that we need to do. Okay, that we had discussed already. Few examples we'll discuss, flow sheets we'll discuss for the metals. So first one is extraction of copper. Write down. Heading, write down extraction of copper. So what you need to memorize here, first of all, that what ore we use for the extraction of any metal. Okay, since we are discussing copper, so copper ke liye we use what? We use copper pyrite ore. We have many minerals, but the mineral that we use for extraction is the ore, and that is copper pyrite. Okay. Flow sheet is what? The flow sheet you see. You also copy this down like this only. You don't, because if you go to write down the theory for each step, it will take a lot of time and not that required. Okay. Suppose if you do for other metals also on your own, to write down in this manner only, flow sheet, so that once you go through, you will understand it properly, and revision will be easier in that way. So we take this ore, that is copper pyrite. Okay, copper pyrite, CuFeS2. And what we did the grinding. Okay, crushing also we call it as. Terms may be different. English word you can understand. Grinding, crushing. So crushing and sieved. Sieved, you understand, no? Filtering, right? Like what are the larger impurities we have that you can easily remove. So hand picking is one of the way. Another one is sieving. We can filter it, right? Sieves we can use for that purpose. That's the next one. Crush, small size, sieved, whatever impurities we can remove, we'll do that. And then we'll move on next. That is the concentration of ore. So here again you see what we need to do. Concentration of ore, which we also called as dressing. Dressing of ore. dressing of ore. What method we use? This is important for you to memorize. The method we use is froth flotation process. Froth flotation. Now, since we have discussed this in detail, so I'm not going to discuss this again over here. That is why I've discussed in general. What is froth flotation process? That is what we are going to use over here, based on obviously the property of metal and impurity. So here we are using froth flotation. Okay. So in froth flotation, you see we add pine oil, right? Why we add pine oil? Why we add pine oil? To generate froth.
Increase
No.
vector.
Yes. So to increase the froth, like to generate froth, large amount of froth you require, right? And one more thing we add into this, that is potassium or sodium xanthate. Correct. So the froth flotation process, just go through once, you'll get it what all things we have over here. So in short, I'll just write down here, not in detail. So we have powdered ore, correct? I'll just change the color. So a little bit of understanding you must have, like the way we have discussed the general process, but eventually you have to mug this up. There's no other way, right? So powdered ore, H2O, we add pine oil to generate froth, and air also will pass through it. It converts into the sulfite ore in the froth, in the froth, sulfite ore in the froth. Okay, we add pine oil, potassium xanthate, sodium xanthate we can add, and we agitate it, mix it properly, the impurities settle down. So in short, stepwise I'll write down here. So we add pine oil, detail we have discussed. We also add uh, potassium xanthate or sodium xanthate. Xanthate, and the mixture will agitate, right? Or we agitate, you can say, or we can, rotate the what we have there, paddle, right, in which there is a blade, so that we can mix the entire mixture properly. So we'll agitate it, right? When you agitate it, whatever impurities we have, not all obviously, whatever impurities can settle down, the impurities will settle down, and then we can filter out the froth from the top, which contains the mineral, okay, the ore that you have. Correct? Copy this down. Okay, can we move now? Can we go to the next slide? Done, all of you? Yeah. So next step is what? After this, we have roasting. We know roasting will done how? In presence of air or in absence of air?
Presence.
In presence of air. So next step is roasting. So roasting, what we do into this one? The concentrated ore are strongly heated in presence of air. So what happens in this process? You see, all these impurities we have, it get oxidized and remove. SO2 removes. Okay. Some impurities are like arsenic present. Okay, this also combines with oxygen, forms oxide 2As2O3. It is a volatile oxide. It also will escape. Okay, antimony we have Sb plus, we have 3O2. This also forms 2Sb2O3. All these are volatile oxides, right? So all these escapes into the atmosphere. So we'll choose the process, the steps, the process based on the impurities present, so that we can have the maximum advantage of a given process. Okay, since all these are forming volatile oxides, can escape into the atmosphere, we'll use this roasting. Correct. So copper pyrite that you have, the reaction would be here CuFeS2. CuFeS2 reacts with oxygen, because we are adding oxygen in this reaction, converts into sulfite first, Cu2S Fes plus O2, and then further it converts into the oxides, Cu2O. This converts into FeO. Overall, in roasting step, we'll get the oxide of copper here. Right? Then the entire mixture here will send this into the blast furnace. Blast furnace is again the machine, the device we use for the process of smelting. Okay, removal of impurities again. So we'll send this into blast furnace. This we haven't done, okay, because it is not required. Like the process is smelting only, but we used to have it in a machine called blast furnace. Okay, the device, entire device is blast furnace. So we send this into blast furnace for smelting. Smelting in blast furnace in presence of air. So what happens here? Iron sulfide, you see, Fes plus Cu2O converts into FeO, Cu2S. This is one reaction which happens there. Further, this Fes, in presence of oxygen, the reaction is taking place. So it converts into oxide again and SO2. And then this oxide, FeO, with SiO2, it converts into FeSiO3. What is this SiO2? Could you tell me? This is the slag we have. Remember flux, acidic flux? Yes, flux plus impurity, it becomes slag. Correct. So first, all the impurities will convert into oxide. That oxide combines with acidic flux and it forms slags, and then it comes out. Yeah, right. You're right, Venkat, correct. So in this process, smelting, what happens? We add the roasted ore that we get in this step. Okay, the roasting is done. So ore that we get, we call it as roasted ore. So in this roasted ore, we mix with, we'll add coke and silica. Coke or silica you can add, you will have this reaction. Correct? Now, after this, we have bessemerization. Bessemerization is nothing but the removal of impurities again. Whatever the iron sulfide is left, we need to remove that further. So we'll do bessemerization. For bessemerization also we add silica. Okay, I'll write down next. First you copy this down. The second last step is bessemerization. Bessemerization is done in Bessemer converter. Again, the name of the device, machine, right? Bessemer converter. What we'll do into this? We'll add silica. We'll add silica. Okay. So the reaction is FeS, whatever iron sulfide is left in the previous step, this get oxidized and convert into oxides, sulfur dioxide forms. Then this FeO reacts with SiO2 that we are adding here, converts into FeSiO3, which is again a slag, will remove it. And the copper sulfide that you have, Cu2S, this combines with O2, convert into Cu2O and SO2. Okay. Now this you see, it goes under auto reduction next. What was auto reduction? This Cu2S sulfide and Cu2O copper. This reacts and it converts into Cu and sulfur dioxide removes. Correct? So like this, the copper that we get is 98% pure. Right? We call it as blister copper. Blister copper. Further, if you want, we can do electro refining also in the next step. Electro refining also we can do here. Auto reduction also we can do. Electro refining also we can do here. So tell me one thing in electro refining, because sometimes they ask, what should be the anode here in electro refining? Anode is pure or impure metal? Thin wala or thick wala?
Anode is thick one.
Anode is the thick one and
Cathode
impure.
is pure thin.
It is impure, thick slab, copper slab, right? Cu slab. Cathode is pure thin slab, right? It is pure thin Cu electrode. What should be the electrolyte? Electrolyte must contains which ion? Cu2 plus ion. That is the only condition. So we can take CuSO4 plus H2SO4 electrolyte. Write down there, CuSO4 and H2SO4 electrolyte we can take. So this is the extraction of copper we have. So like this, for other metals also you can do the same thing. You need to understand that what is actually happening. Almost we have done the entire process, how to do the extraction of any metal. One more we'll discuss, extraction of silver. Others, zinc, iron for sure you must go through once through NCERT or whatever book you have. Correct? So extraction of silver, next you write down. This is the smaller one, we can finish it in 5 minutes and we don't have time also after that. So we'll do this. Next, write down extraction of copper. 9th December crash course is starting, right? You know that? Got the info?
Yes, sir.
All of you, I'm asking all of you. Prepared for it? You can type also.
Yes, sir, we got information.
Yes, so yeah, so it will be mostly a problem solving session. Okay. We'll discuss theory also a bit, but you need to come prepare because everything we won't be able to discuss. Right? So whatever chapter is there given for a date, you need to come prepare, revise your notes, at least solve 10, 15, 20 problems, at least 20 problems you must solve, and then come for the class. Then only it will help. Otherwise, it will be like, wasting of time. Right? If you have any doubt, since you won't be able to ask yours every small doubt. No, we'll have a plan of in the entire 11th and 12th grade. right? So we'll do all the chapters mostly, correct? So whatever chapter it is, come prepare for it, all of you. Okay, extraction of silver. It is done by cyanide process. This also they have asked many times. Okay, it is done by cyanide process. Correct, this you must remember, cyanide process, the name. Ore we use, that is argentite ore. The formula of argentite ore is Ag2S. Okay, so we'll take the argentite ore. Grinding is done. We'll take the fine, a powder of it, and then we'll allow this to pass. Allow this to go for the concentration of ore, and the concentration or dressing of ore is again done here by froth flotation process. The process we are using is froth flotation. Froth flotation. So again, pine oil we add air. So froth carrying sulfide particles, Ag2S, will be up, and below the impurities will have. Okay, and then we have a step over here. We call it a cyanidation. This step is based on the property of metal impurity. We can have few changes, but more or less it will be same. Okay, it is nothing but we have just a reaction here. We have Ag2S, argentite ore, which we get after the concentration. So it is the concentrated ore, is allowed to react with NaCN, sodium cyanide. Okay, so it forms a complex compound of NaAgCN2, AgCN2 plus Na2S. Okay, it is the impurity Na2S. So Na2S is further allowed to react with O2 and H2O. 2Na2SO4 plus NaOH plus sulfur is removed here from this. And then we'll filter it, right? So that is filter it, the next step. We'll filter it, we'll get the filtrate. To silver here, NaAgCN2, from this silver will get precipitate with the help of zinc. We'll add zinc over here. So the reaction would be 2NaAgCN2 plus Zn. It gives Ag forms and we'll get Na2 ZnCN4. We'll get the black precipitate of silver here. Black PPT of silver. Right? Zinc is more electropositive, so it can displace silver here, and we'll get silver. Done?
1 second, sir. So what will we do with the black silver?
No, this is we'll get the black precipitate of silver. Further step is left now.
Oh, okay, sir. 1 second.
After this, we add some, alkali solution into it, like KNO3 we can add, so that the impurities are oxidized and will get silver metal.
Oh, okay, sir. Done, sir. Done.
Okay. So after this, what is that noise on your side, Venkat?
We had some plumbing work.
Okay, same here.
Oh, okay, sir.
For me, it is to every day. Like I have shifted into the new apartment, so it's like every day there is some work here and there. So cut, 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 cut every day.
Full wash space and all, they're doing stuff.
So Ag plus KNO3 will have the fusion now. So this black precipitate of it, it converts into silver metal, and all the impurities here will get oxidized, and it will rise as the scum, which we can filter out. The impurities we can remove like that. Okay, so we'll get Ag metal, silver metal after cooling. After cooling, this is the one we have, and the last step in this is again the same thing, that is electro refining to get the more purity of the of the metal. Electro refining to get the more pure form. We'll do this again. Anode here, the same logic that we did. It is impure thick silver metal. Like this question also they ask, okay, impure thick Ag electrode, and cathode is the pure one, pure Ag electrode. Electrolyte will choose in which the silver ion is present, like we have AgNO3 plus HNO3 solution we'll have here. In this, the pure silver deposited at cathode. Okay, so this is it. Like iron, at least iron you must do. Iron and zinc you can do. Two more. Okay, we'll have this steps only. If you revise 2-3 times, you'll be understanding this, how to do this. But again, you will forget, okay, because the things like this only. This kind of chapters, you should revise before a week of exam. Definitely before a week of exam. Like this one, we have polymers kind of chapter. Surface chemistry is also of similar category. But a few things we can understand in surface chemistry. Right, these kind of chapters you should revise in the last minute. Okay, guys. So fine. We're done with this chapter. Next class, we will start with surface chemistry. Probably we'll finish it next class. Don't know. We'll see. Otherwise, next to next class definitely we'll finish the entire syllabus. Okay. So we have time. 9th of December we are starting the crash course. So after finishing surface chemistry, we'll probably taking practical organic chemistry. We haven't done, no. Like those methods, Zildal methods, Dumas methods and all. It was there in 11th grade, I guess. We haven't done. So not much important, but yes, we'll finish it off since we have time. So we'll do it also. It is a concept of mole concept you need to apply, not much. It will take like 1 or 2 hours, not more than that. So we'll do that also. Correct. Fine, guys. Thank you. Take care. See you in the next class.
Thank you, sir.
Thank you.